Welcome back to Part 7, Designing a Database Demonstration. In this demonstration, we're going to design a database to support a course roster system for our university. The database design will need to model students, courses, and their relationship to each other. That is, the ability of students to enroll into courses. We'll also need to capture unique NUIDs to track students, and we'll need to be able to support the ability to email students about updates in their enrollment. So we'll need to model the fact that one student can have multiple emails. First, let's create a table for students. Let's also include a middle name, but some students might not have a middle name, so let's make it optional. Remember that we also need to model the NUID. At UNL, the NUID is an 8-digit number used to uniquely identify every single student. We could make this into a regular integer. However, that would not prevent anybody from inserting invalid NUIDs, for example, negative numbers. Furthermore, many NUIDs start with a 0. Some start with a double 0. It might be more appropriate to make this column into a varchar instead of a regular integer, so that we can capture those leading zeros. Recall that NUIDs must be unique to every student. Let's put a constraint on the database that enforces that. We could also put a constraint on this column to enforce its length. In particular, all NUIDs are exactly 8 numeric characters long. MySQL Workbench is complaining about the syntax here, but it is correct. However, on some database management systems, check constraints are not enforced. For example, in MySQL, the creation of this table will work, and the check constraint will be parsed, but it's not actually enforced in any of its engines. Other RDBMS systems, for example, SQL Server and Postgres, would enforce this check constraint. Another peculiarity, at least with CSCE's MySQL installation, is that the default character set is not case sensitive. We can fix this by enforcing a case sensitive character set. There are many other options, including full UTF-8 support, but again, various management systems may or may not support these character sets. Now let's take care of the email table. We now need to associate the email table to the student table. There should be a one-to-many relationship from the student to the email table, or equivalently, a many-to-one relationship from the email table to the student table. To achieve this, we need to put a foreign key into the email table that references the student record that the email record belongs to. Following our conventions, we'll name it after the primary key of the table that it refers to, and associate it as a foreign key. Let's go ahead and run this script now to make sure that it works. And both tables have been successfully created. Let's now take care of a course table, which should be pretty straightforward. Here we've designed our course to have a primary key, a subject, and a number, which are just 4 varchar characters. This is to model how UNL numbers courses, typically with a 4-character subject number, such as CSCE, and a number for the course, which can include non-numeric characters, for example 156H versus 156. So we've made both of these varchar fields. We also support the title of the course and a short optional description of up to 4 kilobytes of data. Let's go ahead and make sure again that these tables can be created correctly. This time it failed because the table student already exists from our last run. Recall that we can use a conditional drop table to remove the tables and then recreate them. Let's do that up here. It still didn't work. Recall that the student table is referred to by the email table. We had to create the student table before the email table could reference it. Likewise, when we're deleting it, we would have to delete the email table because it references the student table first. Once no table references the student table, it can be deleted. And the entire script should run without problem now. Let's bring together the student table and the course table. One student can enroll in multiple courses, and one course should be able to have a roster of multiple students. Therefore, between these two tables, we want a many-to-many relationship. We will do this by creating a join table called enrollment. We need two foreign keys, one to the student table and one to the course table. In addition, let's also go ahead and model the fact that a student can enroll in a particular course in a particular semester. After all, students may want to take a course such as an internship multiple times in different semesters, or they may end up retaking a course. But how do we model the semester? We could model it as a varchar character, labeling them as spring 2016, fall 2016, spring 2017, and even summer courses. Unfortunately, if you model it as a string and attempt to use default sorting algorithms, all the fall semesters will appear before all the spring semesters because F comes before S. It's much better to have what's called a total ordering, so that when we naturally order it, all the semesters would be in temporal ordering. That is, fall 2016, summer 2016, and then spring 2016. To do this, UNL uses a 4-digit code to represent the semester. This isn't the best solution. The 4-digit code actually is quite limited. The first digit is always 1. The next two digits are the year in which the semester begins, and the last digit is the month in which the semester begins. In other words, we would never be able to model any semester that begins in October, November, or December. In addition, it appears that some people did not learn their lessons with Y2K. In any case, it's what the university uses and it's what we'll go with. Let's go ahead and add our drop statement and see if this script works. Recall that the enrollment table refers to both the student and the course table, so it would need to be deleted before either of those two tables. However, there's no relationship between the email and the enrollment table. Any delete order would work with those. And all the tables are successfully created. Let's think about more constraints with respect to the enrollment table. You wouldn't want a student to enroll in the same course in the same semester multiple times. If we would consider it bad data if a student enrolled in the same course in the same semester multiple times, then we should put a constraint to prevent such a situation. The uniqueness constraint would be on the combination of a student ID, a course ID, and a semester, because certainly we would want to allow one student to enroll in the same course in different semesters. So we need to capture all three of these columns here. Now that we've created and saved the database, let's go ahead and generate an ER diagram using MySQL Workbench. And as you can see, we've successfully created the database. There is a many-to-many relationship between the course and student table, realized by this join table here. There is a one-to-many relationship with the email table through the student ID foreign key. We've successfully solved all the problems with our original data that we looked at when we started this series. Pieces of data are now organized and have a specific type. There's no duplication of data because we normalized the database. Entities are represented by IDs ensuring identity so that Tom Waits is the same entity as T Waits, and there's no inconsistency about their name representations. Data integrity is enforced. There's only one NUID per student. This was not possible with a flat file. Relations are well defined. A student has emails, and a course has students, and a student has courses. The normalized data from the original example is depicted here. I hope you've enjoyed this series on SQL and database design. Subsequent videos will examine how to programmatically access data in a database.